Yeah, I'm Andrea Francesio from Glasgow University, and the topic I'm going to talk to you about is the effect of soluble carbohydrate diets on reticuloruminal pH and motility, and how these relationships can be seen in a non-traditional way. So, we are all well aware how carbohydrates are important as a source of energy for cows, but also how carbohydrates bring along the risk to drive ruminal pH to dangerously low level. And historically, sugar has been linked to a higher degree of risk to trigger acidotic disruption in rumen metabolism, but evidences available in literature are not univoc. So in different trials after the addiction of sugar to the diet, pH did not change compared to starch diet, or decrease, or in some other trial even increase. So are ruminocentesis and pH actually the best way to effectively assess rumen health? Well, rumen pH definitely is still considered one of the most objective and reliable parameter to evaluate rumen health. However, many different factors can affect ruminal pH, and also it's very difficult to link mild acidic value of a ruminal pH to a very well-defined pathologic process. Trying to overcome these issues, joint effort from academic and industrial world brought us some interesting tools. So on the left-hand side of the screen, you can see our commercially available boluses. We used that in our trial, and we set it up to collect data every 10 minutes, and particularly this bolus recorded ruminal pH, ruminal temperature, and motility. On the right-hand side on the screen, there is a prototype built up by Strathclyde University at Glasgow, specifically designed to monitor rumen motility. The difference between these two motility records was the frequency. Our bolus was set up to record motility every 12.5 Hertz, with a frequency of 12.5 Hertz. This means that every 10 minutes we have not just one measure, but something like 7,500 data points. So given these two premises, the two hypotheses we wanted to verify was, number one, diet type would have a differential effect on ruminal motility, pH, hematology, and biochemistry, and number two, continual measurement boluses would provide an effective way to measure reticuloruminal health. So the trial involved 6 adult non-lactating rumen fistulated Jersey cows, which were fitted with the 2 boluses described before through the rumen cannula. The study lasted 63 days, divided into 3 experimental periods of 21 days each. During the first 2 weeks of each experimental period, all the animals were fed with a control diet. In the last week of each experimental period, the animal divided in pairs were allocated to 3 different diets. One was the control diet, and the other 2 were 2 diets designed to trigger a mild acidotic challenge. The first diet was high in starch, while the second diet was high in sugar. However, the diets were high isonitrogenous and high isoenergetic. So the boluses went in on the first day of the experimental period and came out the last days and stay in all the way through. But blood samples were taken on the first, on the second, and the last day of each challenge week, for a total number of 9 blood samples through the entire period. Blood samples were used to evaluate inflammatory and energetic status of the cows. How did we analyze the data? So from the pH boluses, obviously data were analyzed only from data coming from the challenge week, and none of the data was normally distributed. We did a very basic descriptive statistic. We calculate median, minimum, maximum, and standard deviation PA for each cow for each hour of each days. And the Kruskal-Wallis rank sum test was used to determine whether hours of the day or diet had a significant effect on these parameters. Due to the high frequency of of recording from the motion sensing boluses, we needed to group data over a time lapse of 1.5 seconds, and that was done to improve the curve definition. Even these data were not normally distributed, and the rhythm and the amplitude of the different peak was used to recognize which were the data related to rumen contraction. That was necessary to discriminate between normal rumen contraction and overall movement from the cow or other movement that act as a background noise in this case. So whenever a cow lay down or get up or walk about, the bolus would have recorded that, and we needed to discriminate this movement from reticuloruminal contraction. Once the right peak were identified, amplitude and intercontraction period were calculated, and again, Kruskal-Wallis test was used to determine whether diet had an effect on these two variables. As we said before, blood samples were collected on the first, the second, and the last day over each challenge week. And again, data were not normally distributed. Delta values was calculated between time point 1 and time point 2 and time point 1, and as well between time point 7 and time point 1. Kruskal-Wallis was applied on delta values to see whether diet and time point had an effect on blood results. So let's take one more minute to explain this slide. This is a summary of all the data collected during all the challenge weeks from all the cows, plotted by diet and over a 24-hour period. The three diets are the control, the starch, and the sugar, and there is a day length on the x-axis. The area between the two red line is the time when the food was likely to be delivered, and it is between 7:30 and 9:30 in the morning. And the horizontal line is our lower threshold or lower cutoff. It has been marked at 5.6 using the lowest point reached by one cow fed with controlled diet. And this is quite an interesting feature of continual monitoring sensors. We would be able to set up target based on actual animal performance on farm or within the group, rather than trying to fit our animal on a cutoff setup elsewhere. So how did the animal behave? Both the challenge diets successfully brought the pH lower than our cutoff, although they did at different times during the day, and they appear to stay for a different time below that threshold. Sugar diet was the diet that had the lower nadir. These two box plots are a summary of the diet effect over the amplitude and the intercontraction period registered by the motion sensing boluses. So on the first box plot, we have again the three diet and their effect over the amplitude. We can see how starch diet statistically significantly increase the amplitude of reticuloruminal contraction, and on the opposite side, how starch statistically significantly decrease the amplitude of the reticuloruminal contraction. Oh. The second box plot is a summary of the effect of the diet over the intercontraction period. And in this case, both diets act in the same way, reducing the intercontraction period, namely increasing the reticuloruminal contraction rate. This table is a summary of the blood results, and the most interesting results we got belong both to the starch diet, and which appear at time point 2 for lymphocyte and neutrophil. We have an increase in neutrophil at time point 2, and at the same point a decrease in lymphocyte. This was interpreted as a detectable sign of inflammation, which was present, interestingly, only with one diet, despite the decrease on pH seen on both diets. So what conclusion can we get from our study? pH declined with both diets. Both diets were successful to cause our mild acidotic challenge. The lower point was reached with sugar diet, but the neutrophil count that suggests a stronger inflammatory response was seen with the starch diet. Motion sensing boluses show promising feature, and they seem to be able to discriminate among diets. However, they are a developing technology and they need more work to better filter and analyze data. And in the end, sugar and starch diet compared to control diet had differential detectable effect, and also between the two diets had different detectable effect on pH curves, blood results, and contraction rate. What we would like to do in the future, we would like to compare our data set on the model developed by Denwood et al. Basically, this model describe a normal diurnal variation of ruminal pH. We would like to see how well this model fit to our data set, especially from control cows, and then compare this model with the challenge diet and see how the distribution and the entity of the residual we expect to find. If any of you remember what Professor Hotzel said this morning about cutoff, in this way we would not have just one cutoff, but see over the 24-hour period of the continuous variation of pH against, in this case, the generalized additive model, and see how this variation can explain poor health performance or poor production performance from cows. After that, it would be good to compare this relatively new method to diagnose SARA with more traditional method of SARA diagnosis, and more in the short term to analyze the pH decay curves for the two diets in the 6-hour post-feeding. Motility bolus, as I said, they are still a developing technology, so better and more precise algorithms are necessary, and we are also thinking about using a gyroscopic sensor in place of accelerometer, just as the same different source of the same data set. Just before finishing, I'd like to thank different people which made my work possible with their work, and thank you as well for your kind attention. I will be happy to answer to any further question at the best of my possibility. Thank you.